Okay, let's start today's lecture. So yesterday we had discussed about torsional oscillations and how to analyze torsional oscillations. Different modes of torsional oscillations can be there, local modes and common mode. Using eigenvalue analysis, we can analyze the pattern of oscillations. Using eigenvalue, we'll find the frequency of oscillations in each mode, and using eigenvector we'll get the mode shapes of these oscillations. Now coming to the subsynchronous resonance, till now we have seen subsynchronous oscillations and how subsynchronous oscillations happen. Another phenomenon which is an extension of this is subsynchronous resonance. Before going to subsynchronous resonance, let's see let's reiterate what we have seen yesterday using a multi-mass system. Here you can see this is a high pressure turbine, this is an intermediate pressure turbine, this is low pressure 1, low pressure 2, this is a generator, and if there is a rotary exciter then we will have one more mass. This need not be there, but if there is a rotary exciter then this will be also there, rotary exciter. Now this has 6 masses. This is a multi-mass system with 6 masses. This can have 5 modes of torsional oscillations. Torsional oscillations. You can see the shafts here: 1, 2, 3, 4, 5. Okay, and one mode of common oscillation, or one common mode oscillation. Common oscillation, which means common oscillation is the oscillation considering all the masses moving together. Now, in what context these oscillations are amplified, that is what we are going to see. Then only we'll term it as resonance, subsynchronous resonance. Say we have the generator here connected through a transformer and to a line. So the line we are assuming as a combination of R, X and a series capacitor C, because we are compensating the line using series capacitance so that the equivalent impedance could be reduced and the voltage profile can be improved, or rather the voltage drop can be reduced and the voltage profile can be improved in general. So this is the infinite bus. This is the infinite bus. Now the receiving end voltage, basically the receiving end voltage can be improved. Voltage can be improved. Okay. Yes. Now say we have a change in mechanical torque in the multi-mass system. So this is a multi-mass system which is basically here. The generator is only connected to the grid, but if this is a steam based power plant, then this is a multi-mass system like this, right? Like this. So we can have disturbance on this system from the electrical network side or the mechanical side. So if it is from the mechanical side, we take it as the change in mechanical torque, Tm, delta Tm. Okay, so we have a change in Tm. Then these 5 modes of oscillations, torsional frequencies are excited. 5 modes of torsional frequencies are excited, and it will be reflected on the generator speed. Definitely it will be reflected on the generator speed. But it can be momentary, because after some time it may settle down to another steady state value, and again these speeds the speed of each mass may be equal after some time, after getting back to the equilibrium state. Now, as there is a change in momentary speed of the generator rotor, the stator induced EMF the stator induced EMF may also change because of that momentarily. And because of the change in stator induced EMF, the current will change. The stator current will change. But the stator is connected to the grid. It is synchronized with the grid. Now, if the currents produced in the stator or currents the currents injected to the grid, if they have the same frequency of the excited frequencies of mechanical shaft oscillations in the torsional oscillations, if this frequency in the electrical network is near to the frequency of torsional oscillations, then what can happen is that these torsional oscillations may be excited or amplified, and it may go unstable. Or rather, the electrical torques or the disturbance torques generated in the electrical side, network side, may interact with the mechanical torques in the generator in such a way that the torsional oscillations grow in amplitude and go unstable. Now, normally this is seen when there are two conditions. Normally this is observed when the torsional oscillations are of subsynchronous frequencies, or synchronous frequency is 50 Hz, so less than 50 Hz. So torsional oscillations frequencies are of subsynchronous in nature. And the second condition is when the transmission line is series compensated. So in this condition, we observe that the currents generated in the grid because of the mechanical disturbance in the multimass system affecting the momentary rotor speed, these currents have frequencies near to the natural torsional frequency of oscillation, and this will enhance the amplitude of torsional oscillation, and it may go unstable. The shafts may break, or the twist of the shaft may be unbounded. Now, this phenomenon is known as subsynchronous resonance. In fact, the series compensated network may have a resonance frequency, because basically this is LC, right? This is LC. So may have a resonance frequency which comes closer to the torsional frequency. Torsional frequency is this one, right? Torsional frequency. Near about the natural frequency of torsional oscillation, and enhances the torsional oscillations. So this is a kind of cause and effect explanation, because the cause is Tm, which happens from the mechanical side. The effect is Te, right? Then Te itself acts as an input to the mechanical side, input or the disturbance to the mechanical side. So again, a disturbance happens here, then the rotor speed will change. It may disturb the current that is flowing through the network, the series capacitor compensated network. Then again some Te is produced, so it may interact back. So this is an interaction, a mutual interaction between the turbine generator system and the electrical network. Now, in general, we are not going to the detailed mathematical model. So in general, it can be like this. This is a turbine generator system. Now this is connected to the electrical network, right? Electrical network, right? Now from the turbine generator system, we have del G and omega G, angular velocity of the generator and the power angle of the generator. Power angle in the sense, it's electrically it's the voltage angle, or mechanically we can say that it's the relative displacement between the physical rotor axis and the synchronously rotating frame. So del G and omega G, basically these are disturbed. These two variables are disturbed with a disturbance in Tm, delta Tm. Now this will affect the current. So delta I will come into picture. Basically that can be decomposed into ID and IQ. Okay, now the torque generated, the electrical torque generated is phi psi d IQ minus psi q ID. So when ID and IQ are changed, electrical torque will change. Delta TE will come into picture. So the changes in electrical torque will further affect. That means ID and IQ are changed. There is a change in electrical torque. This may interact with the shaft oscillations or the torsional oscillations in the system. Changes in electrical network affects these variables ID and IQ, which in turn affects psi d and psi q. Okay, psi d and psi q. So this is the interaction between electrical network and the mechanical system which causes the subsynchronous resonance.